So welcome to the next class of probability. So today we'll keep talking about the law of large numbers. Okay, so the point with the law of large numbers is the question is what are the hypotheses that we need? Okay, so basically we're going to take Sn, the sum from I equals to 1 up to n of xi, and we want the expectation of xi to be equal to mu. Then what are the extra hypotheses that we need of Sn over n to converge to mu, and also in which sense? Okay. So last time the theorem that we showed was pretty similar to the one that we are going to be showing now, is that assume that xi is a sequence of id variables, random variables, with expected value of xi equals to mu. Then Sn over n converges in probability to mu. Okay, so last class we showed this theorem under the hypothesis that the variance of xi is equal to k, which is bounded. Okay, so if the variance of every xi is equal to k and it's bounded, then we can actually have this. We can show it from last time just using Chebyshev's inequality. Like that, we show this theorem under the hypothesis that this by Chebyshev's inequality. Okay, so this class, what we're going to try to show it is without the use of Chebyshev's inequality, by using it from last class, using what we knew from last class. So instead, okay, so proof. Okay, so instead of considering xn, we consider yn, which is equal to the indicator of the modulus of xn less than, let's say, L times xn. So the idea is that yn for every L positive, okay, so here we still need to pick L positive. Okay, so we still need to pick L positive, so we can actually choose whatever we want. But from last class, okay, before from last class, what we should notice is that the variance of yn is less than L squared for every n. Therefore, the sum from I equals to 1 up to n of yi divided by 1 over n converges to the expectation of y1 in probability. Okay, so the idea is now to take this L to infinity, use the by last class, use the result from last class to have this convergence, and then check that when L goes to infinity, this converges to the expectation of x1, which is equal to mu. Okay, so all right, so the first thing that we should notice is that the expectation of, let's check, expectation of y1 converges to the expectation of x1, which is equal to mu. Okay, and now I'm gonna wave my hands a bit, but the point is that the definition of expectation requires absolute convergence. Definition of expectation requires absolute convergence of the sum let's call it k in the image of x1 f x1 k, or the integral x fx1 x dx. So in particular, if we start limiting the integral to be, what we need is the sum from k in the image of x1 with k less than L of k f x1 k converges when L goes to infinity to the expectation of x1, and the same for the integral. So in particular, when we take L large enough, so in particular for every epsilon positive and for every delta positive, there exists an L such that the expectation of yi is minus mu, which is the expectation of xi, is less or equal than, let's say, epsilon times delta over 8. Okay, so the point is that we want to show convergence in probability, so we need to fix an epsilon positive, and so for every epsilon positive and for every delta positive, we have this this property here for an L, with an L which is large enough. So now what we're going to do is we're going to take the difference. We're going to take the difference, the sum of xi, I equals to 1 up to n, over n minus mu, is going to be less or equal than adding and subtracting what we need, which is going to be the sum of xi, I equals to 1 up to n, over n minus the sum from I equals to 1 up to n of yi over n plus the sum of yi I equals to 1 up to n over n minus the expectation of y1 plus the expectation of y1 minus the expectation of x1. Okay, so this is a pointwise bound. So this is a pointwise bound. And we realize that by the choice of L, this is less or equal than, let's say, epsilon times delta over 8. So now, if if we want to look at the probability, so now the set that the sum, so we now want to look at the set of the sum of xi, I equals to 1. So Sn over n minus mu is bigger than epsilon. So this is bigger than epsilon. The set that this is bigger than epsilon is going to be contained in the set that either this is bigger than epsilon over 4 or this is bigger than epsilon over 4, because this is a lower order term. So if both of them are less or equal than epsilon over 4, then this cannot be bigger than epsilon, because the sum of these three things is actually less than epsilon. So this is contained in the sum of xi, I equals to 1 up to n divided by n minus, so this is the set of the sum of yi, I equals to 1 over n, bigger than epsilon, union, so this is a containment, union the sum of yi over n, I equals to 1 up to n, minus the expectation of y1 is bigger than epsilon. And here over 4, let's say, and over 4. So the point is, if both of these numbers are less than epsilon over 4, epsilon over 4 plus epsilon over 4 plus epsilon over times delta over 8 is going to be less or equal than epsilon. So we cannot be in this set. Okay, and this is assuming delta less than 1. Okay, and now now the point is to check, okay, so the right hand side here, the probability, the limit when n goes to infinity of the probability that the sum of yi up to n divided by n minus e of y1 is bigger than epsilon is equal to 0. Okay, so if we take this limit of this guy, this is equal, of the probability of this guy, this is equal to 0. So if we can show that the limit of the probability of this is as small as we want, then we have shown the convergence in probability. So now what we need to check, so this is term, let's say v, So this checks B. And now for the term A, we have that the probability of A. Okay, so probability of B. The probability of A is equal to the sum of xi minus I equals to 1 up to n of the probability of this is bigger than epsilon times n over 4, but because xi and yi are all IID, we can actually say that this is equal, or actually, well, so sorry, we have here an absolute value outside. So here that we have that this is less or equal than the probability of the sum of xi minus yi is bigger than epsilon times n over 4, and this is the sum from I equals to 1 up to n. But this is less or equal, and this is Markov's inequality. That Markov's inequality tells you that the probability that you're larger than a number is going to be less or equal than the expected value of the sum from I equals to 1 up to n of xi minus yi divided by the number. So in this case would be epsilon times n, and there is a 4 in front of this. Now xi and yi are all xi's are all identically distributed and yi are identically distributed, so this is equal to 4 times the expectation of x1 minus y1 divided by epsilon times n. So the n goes with the n, and we get this. And so the point is that this is actually less or equal than delta. So we can, this is by picking. So the point would be if L goes to infinity, this goes to 0. Okay, so the way that we chose y1 was to get that the expectation was the right less or equal than epsilon over delta, epsilon times delta over 8, but we can just pick it as being the expectation. So here it would be the expectation of y1 minus x1, which is what is left of xn outside xn less than L. We can actually check that we can make this to go to 0 as L goes to infinity. So basically what we have gotten is that the probability that xn minus x is the sum Sn over n minus mu is bigger than epsilon, the limit when n goes to infinity, is less or equal than 4 times the expected value of x1 minus y1 over epsilon, and taking L to infinity, this goes to 0. Okay, and that's the proof of how we actually take care of this without using the variance. So, but here the remark would be, here we got rid of the variance hypothesis, but now we assumed that all the random variables are identically distributed. Okay, so usually if you give up with some hypothesis, you need to bring some other hypothesis back. Okay, so now let's look at the strong law of large numbers. Okay, so the theorem, strong law of large numbers, is that Sn over n converges to mu, and now almost surely. Okay. So we're not going to give the proof in general. So this result is true. The result. So remark. The result is true in general with no other hypothesis on variance or integrability or finite moments. Okay, so so the result is true in general with no other hypothesis on variance or finite moments, but the proof is much simpler if we assume, so here I guess I should write it, xi is a sequence of IID such that the expected value of x1 of xi is equal to mu for every I. Okay, so these guys are independent and identically distributed, and so the result is in general with no other hypothesis of variance of finite moments, but the proof is much simpler if we assume the expectation of xi to the fourth to be finite. Okay, and so we're actually going to do it assuming this. So now we're going to need the following lemma, which is how we're going to exploit this condition. If for every epsilon positive, the sum from n equals to 0 up to infinity of the probability of xn minus x bigger than epsilon is finite, then xn converges to x almost surely. Okay, so let's look at the proof. So this one was something that perhaps was a little unclear last class, so let's try to go over it again. So xn xn converges to x almost surely if the probability of the events of the omegas in omega such that xn of omega converges to x of omega as n goes to infinity is equal to 1. Okay, but this is the same. Okay, so this is the same as saying that the probability of the intersection of epsilon positive of the union of n0 in n of the intersection of n larger than n0, the probability of all of this set is of this set xn minus x bigger than epsilon, smaller than epsilon, is equal to 1. So, but now this is, whenever we take the epsilon smaller and smaller, we have a nested sequence of sets which are given by these unions of intersections. So in particular, this is equal to 1 if and only if the probability of the union, okay, so this is if and only if, for every epsilon positive, the probability of the union of n0 in n of the intersection of n larger than n0 is xn minus x less than epsilon is equal to 1. Okay, so if we can show that this is true for every epsilon, this is equivalent to this, which is equivalent to almost sure convergence. Okay, but now what we can realize is by taking complements, this is equivalent to the, for every epsilon positive, the probability that the intersection n0 in n of the union n bigger than n0 of xn minus x, now bigger than epsilon or bigger or equal than epsilon, is equal to 0. Okay, so if we can prove this, we have almost sure convergence. Okay, so if we can prove this, this property, we imply almost sure convergence. Okay, but what we realize is that, by hypothesis, okay, so what we try to calculate is the probability of the intersection of the union, but by the continuity of probability. Okay, so this is a nested sequence of sets. Whenever n becomes larger, this becomes smaller and smaller. So this is equal to 0 if and only if the limit when n0 goes to infinity of the probability of the union n larger than n0, xn minus x bigger than epsilon, is equal to 0. But now what we realize, okay, so here we have used the continuity of probability, but what we realize is that this thing is less or equal than the sum from n larger than n0 of the probabilities of xn minus x bigger than epsilon. So here what we have used is that the union, the probability of the union is less or equal than the sum of all of them. So in particular, now we have to take the limit when n0 goes to infinity. But the hypothesis the sum of n equals to 0, n equals to 1 up to infinity of the probability of xn minus x bigger than epsilon is finite, implies that the limit when n0 goes to infinity of the sum from n equals to n0 up to infinity of the probability of xn minus x bigger than epsilon is equal to 0. Okay, and this proves the theorem that we were trying to say. So if we have that the sum is finite, then xn converges to x almost surely. Okay, so let's try to use this to prove the strong law of large numbers. So what we're going to do here is to actually calculate the fourth moment of Sn. Okay, so proof. And this I'm not going to show, but you can actually show it yourself. Without loss of generality, assume that the expectation of x1 is equal to 0. Okay, so mu is equal to 0. And now, so let's think that now the expectation of xi to the fourth is less or equal to c, which is finite. So in particular, the expectation of 1 plus xi squared, xi squared, so of the second moment, is going to be less or equal than the expectation of 1 plus xi to the fourth, which is less or equal than 1 plus c. Okay, so if we have fourth moment bounded, implies second moment bounded, and this is true in general. And so what we are going to try to calculate is the expectation of Sn to the fourth. Okay, so this is similar to when we try to take the variance of Sn. So the expectation of Sn to the fourth is going to be equal to the expectation of x1 plus xn all to the fourth. And now the point is that we need to distribute the fourth power. We distribute the fourth power using that xi is independent and identically distributed. Because what we're going to get is we're going to get n terms of the expectation of x1 to the fourth. And the point is that they're all identically distributed, so it doesn't matter if it's x1, x2, x3, x4, they all have the same fourth moment. So we can just multiply by n to denote this. Now, we're going to start getting cross terms that depend on more than one of the random variables. The next level, we're going to get n times n minus 1 terms of the expectation of x1 cubed times the expectation of x2 here. So here what we are using is the independence to say that the expectation of the multiplication is the multiplications of the expectations. So in particular, what we have by assumption is that the expectation of x2 is equal to 0 by assumption. The other terms that we're going to be getting is of the form n times n minus 1 times n minus 2 divided by 2 of the expectation of x1 squared times the expectation of x2 times the expectation of x3, which again, this is equal to 0 and this is equal to 0. And the other thing that we're going to get is plus n times n minus 1 divided by 2 of the expectation of x1 squared times the expectation of x2 squared. Okay, so this is when the fourth power we get 2 times on x1 and 2 times on another variable. They are all the same, and then we count how many of them we have, and this is given by n times n minus 1 divided by 2. And the last term is n choose 4, which is the quantity, the amount of ways that we can choose 4 of these variables, of e of x1 times e of x2 times e of x3 times e of x4. But again, this is equal to 0 because the expectation of a random variable, we assume it to be 0. Okay, so in the end, what we get is that the expectation of Sn to the 4 is equal to n times the expectation of x1 to the 4th plus n times n minus 1 over 2 of the expectation of x1 squared. So in particular, this is less or equal than n times c plus n squared times c plus 1. So in particular, all of this is less or equal than n squared c plus 1. Okay, but now if we take the expectation of Sn over n to the 4th power, this is going to be less or equal than c plus 1 squared over n squared, because the 4th power makes this come out with a power n to the 4th, multiplied by n squared, we still get n squared in the denominator. Okay, now we use Chebyshev's inequality. Okay, this is the generalized Chebyshev's inequality. that tells you that the probability that Sn over n in absolute value is bigger than epsilon is going to be less or equal than the expectation of Sn over n to the fourth over epsilon to the fourth, which is which is less or equal than c plus 1 squared over epsilon to the fourth n squared. Okay, so our objective is to show Sn over n converges almost surely to 0. But by the lemma, it is enough to show by the lemma, it is enough to show that the sum from n equals to 0 up to infinity of the probability of xn minus, so the probability that Sn over n bigger than epsilon is finite. But this we have just shown is less or equal than c plus 1 squared over epsilon to the fourth n squared. So in particular, this is summable, which implies Sn over n converges almost surely to 0. Okay, and that's the proof I wanted to show today.